Water is one of the most essential natural resources, playing a vital role in supporting human life, ecosystem, agriculture, and industrial activities. Therefore, maintaining good water quality is crucial for protecting public health and preserving the environment. Contaminated water can contain harmful chemicals and pollutants that pose serious risks to both human and aquatic life, making regular water quality testing an important practice. To evaluate the chemical composition of water accurately, analytical chemistry provides a variety of techniques for identifying and measuring dissolved substance. Among these techniques, volumetric analysis, also known as titration, is one of the most widely used methods because of its accuracy, simplicity, and cost effectiveness. It enables the determination of the concentration of specific chemical components in water such as acids, bases, chlorine, and hardness-causing ions. The application of volumetric analysis is essential in ensuring that water meets established quality standards. It is extremely used in water treatment plants to monitor and control water treatment processes, as well as in environmental monitoring to assess the quality of rivers, lakes, groundwater, and other water sources.
Now, let's go to theory of volumetric analysis. Volumetric analysis, also known as titration, is a quantitative analytical method used to determine the concentration of an unknown solution. It works by allowing a solution with a known concentration, called the titrant, to react with the unknown solution, known as the analyte. The reaction continues until the endpoint is reached, which is usually detected by a color change of an indicator. From the volume of titration used, the concentration of the unknown solution can be accurately calculated. Apparatus used. Firstly, burette. Burette is used to accurately deliver the titration into the analyte during the titration process. Next, pipette. Pipette is used to measure and transfer a fixed volume of the analyte into the conical flask. Volumetric flask is used to prepare standard solution with an accurate and precise volume. Indicator is the chemical that change color at the endpoint, showing that the reaction between the analyte and titrant is complete. Finally, conical flask is used to hold the analyte and indicator while the titration is carried out.
Next, I will explain about methodology for water quality testing procedure. First, a representative water sample is collected using a clean container to avoid contamination. Proper sampling ensure that the result accurately reflect the actual water quality. Next, a standard solution with a known concentration is prepared and standardized. This solution acts as the titrant, allowing accurate determination of the concentration of substance present in the water sample. Next, a fixed volume of the water sample is transferred into a conical flask using a pipette. Using an exact volume is important for obtaining reliable and reproducible calculation. A suitable indicator is added to the sample. The indicator changes color when the reaction reaches the endpoint, signaling that the titration is complete. Next, the titrant is slowly added from a burette into the flask while continuously swirling the solution. The titrant reacts with the target substance until the endpoint is reached. Next, the volume of titrant used to reach the endpoint is called the tide value. This value is recorded carefully for further calculation. And lastly, the titration is repeated several times until consistent tide value are obtained. This improves the precision and reliability of the experimental result. Next, I will present about titration technique. First, before starting the titration, the initial burette reading is recorded accurately. This is used to determine the exact volume of titrant delivered. Second, the conical flask is swirled continuously during titration to ensure complete mixing between the titrant and the water sample, allowing the reaction to occur evenly. Third, as the endpoint approach, the titrant is added one drop at a time. This prevents overshooting the endpoint and improves the accuracy of the measurement. Next, the endpoint is identified by a permanent color change of the indicator, showing that the chemical reaction has reached completion. After that, after the endpoint is reached, the final burette reading is recorded. The difference between the initial and final readings give the tide volume. Finally, the tide volume is used in stoichiometric calculation to determine the concentration of the substance being analysed, such as hardness ions, chloride or alkalinity in the water sample.
Now, I will explain the industrial application of volumetric analysis in water treatment plants. First, volumetric analysis is used to monitor water hardness by measuring calcium and magnesium ions using EDTA titration. This is important because high hardness can cause scaling in pipes and industrial equipment. Second, chlorine concentration is monitored to ensure effective disinfection. The DPD colorimetric method is commonly used to determine chlorine levels and maintain a safe residual concentration between 0.2 and 4 mg per liter. This helps eliminate harmful microorganisms while ensuring the water remains safe for the consumption. Third, alkalinity is measured using acid-base titration. A strong acid is added until the endpoint at pH 4.5 is reached. This allows us to determine the water's acid neutralizing capacity and helps maintain a stable pH in water system. Overall, these tests are essential of ensuring that water treatment plants meet safety and quality standards. Volumetric analysis is important for several reasons. Firstly, it helps provide safe drinking water by detecting harmful chemical levels and ensuring proper water treatment. Secondly, it protects public health by reducing the risk of waterborne disease and maintaining safe chemical concentration in water. In addition, volumetric analysis helps water treatment plants comply with national regulation and water quality standards. Finally, it is a cost-effective method because it is accurate, reliable, and suitable for routine monitoring. Therefore, volumetric analysis remains as an essential analytical technique for maintaining safe and sustainable water resources.
From the bar chart included, it shows an example of water hardness measured by volumetric analysis using EDTA titration. So, 4 different water samples were analyzed. The first one is sample A, which is tap water, has the lowest hardness of about 75 mg per liter. The second one is sample C, which is lake water, has a moderate amount of hardness of approximately 95 mg per liter. The third one is river water, which is sample B, shows a higher hardness of around 130 mg per liter. The highest hardness is found in sample D, which is sample 4, which is groundwater, with about 180 mg per liter. This indicates that groundwater generally contains more dissolved calcium and magnesium ions because it remains in contact with rocks and minerals for a longer period. From this result, we can clearly compare the hardness of different water sources. These informations help water treatment plants determine whether additional treatment is required before the water is supplied for domestic or industrial use. In conclusion, volumetric analysis is one of the most important analytical techniques used in water quality testing. It provides accurate and reliable quantitative results by determining the concentration of substances through titration. In water treatment plants and environmental laboratories, volumetric analysis is commonly used to measure water hardness, alkalinity, chlorine concentration, and other important chemical parameters. The results obtained help to ensure that water meets safety standards before it is supplied for drinking, agricultural, or industrial use. Compared with many modern analytical instruments, volumetric analysis is relatively simple, cost-effective, and easy to perform while still maintaining good accuracy. Therefore, it remains an essential technique in analytical chemistry and plays an important role in public health and preserving the environment. That concludes our presentation. Thank you for your attention. Bye.